Hey guys, welcome back. In this video, I want to talk about one important question. So this question has been asked to me by one of the viewers. So I thought I will bring this topic to this particular channel. Mm, so with this, I think I have to start a new series that is related to PRACH. Okay, all the information or all the concepts related to PRACH, I will put it in this particular series. So I hope that's okay. The thing is that even if you see my previous videos like BWP versus carrier aggregation and even SRS versus DMRS. Okay, so these are also asked by the other viewers and many other questions which are asked by viewers I have put on the channel. So if I know the concept and if I bring them as early, I will try to bring it. So you can also post your questions. And I will try to bring them to my channel. It may not be technical always. It can be even since I've started the financial thing, so you can ask those questions as well. Technical, non-technical would be fine. Okay, even if it is motivation also, that would be fine. Okay, so let's get started with the topic timing advanced calculations or timing delay estimation. Okay, so the thing is that let's say we have got two UVs. Okay, so let's say UV number one and let's say UV number two. So let's say this is a base station. Now we are trying to see why do we need timing advance or timing delay calculations. So at G naught B, it has got some time reference. Let's say this is the time reference T0. So G naught B expecting that at the T0 the signal from UV1 and UV2 both of them reaches together. Then only both of the signals can be processed properly. So let's say the signal is traveling and since it has traveled a long distance, it created a delay tau d1. So this would reach a little bit early tau d2. So what is the relation? Tau d1 is actually greater than tau d2, right? So now we expect them to be receiving at T0. Okay, so now what does G naught B do? It calculates this particular delay and informs to the UV that you are having this much delay, so you actually send your signal much advance. So that's where the timing advance comes into picture. So timing delay would be estimated in the G naught B, and when it informs to the UV, it mentions timing advance, saying that okay, you need to advance your signal by this much amount. Okay, I think you've got this clarity. So now the thing is that mm, let me take another slide. Now UV number one. Okay, it was here and it was here and we expected that T0. Okay, this is the G naught B. Now this applied the timing advance correction. Okay, it started much advance. Okay, it started much advance. um, so I will try to write a different diagram in this case to make it clear. Will not write G not B. So earlier what was happening, the thing is that because of delay, so it expected signal as T0, but what happened, this one has reached at this point, okay, tau d1, and this signal has reached somewhere here, so tau d2. So this much delay is there at G naught B. Okay, I will write it right here as G naught B. Now the thing is that once these apply the corrections, okay, let's say these two apply corrections, then what you would see is this starts much early, which means that uh, how do I show? So okay, so it applies the advance corresponding to TD1, so that the signal received will be exactly at T0. Even for this UV number 2 as well, the signal received will be exactly at this point. So at this point both the signals are received simultaneously, okay, at the G node B. So the further processing becomes simpler. This is the expectation. I would say, at UV1 to give the clarity. Earlier, it was, let's say, starting from this point. At the UV number 2, let's say this was starting at this point. Now, because of advance, it was starting here, right? Let's say this is T1, this is T2. Now, advance means this will start much early. Okay, so this much early it has to start. This also it has to start this much early. So it has compared to these two UVs, UV1 has to start much early, whereas UV2 has to start little late. But finally, both the signals should reach the G node B at the same time. Okay. So this is what is called as uplink synchronization, which is required for today's 4G or 5G OFDM systems. Okay. So now, having understood this concept, we will try to get into the more details. An example of 15 kilohertz subcarrier, 20 megahertz bandwidth, right? I mean, I will just go for LTE case for now. You can or 4G. You can similarly calculate for 5G. I will take format 0. Okay, this is a long format, and its subcarrier spacing is actually 1.25 kilohertz. This is subcarrier spacing. Okay, SCS I will write. So this is SCS and this is the bandwidth. So for this one, what is the sampling rate? So Fs is equal to 20 megahertz, right? How many RBs are there in 4G? So 100 RBs. Sorry, how to calculate? We need what is the F50 size which we are using? 2048 into 15 kilohertz, right? So this comes to be 30.72 mega samples per second. This is the sampling frequency Fs. So Ts is equal to 1 by Fs, sampling interval. Okay, I will consider it like I will just say now to make it simpler. I will just take 1 UV signal is transmitting right over the air. What is this? This is analog signal, and this is a time domain signal. Okay, so this analog signal, this is how we have to transmit in the real channel. But when we start doing the processing at the G node B, we do the processing in digital domain, right? So which means that analog signal is converted into digital, and we do digital signal processing. So what do we use for that? We use analog to digital converter, and as I mentioned, we use the sampling frequency, sampling rate this much. Okay. So finally, at the G node B, what I would say, so it is supposed to reach signal at this point, but the signal has reached, after some delay. This is the delay. Now, since we are doing, some kind of sampling, now what do we get? So we get samples, right? So something like this. We get the samples. Here also we get the samples. So between these two samples, the sampling interval is given by Ts, right? From one sample to another sample. Now we going to identify the delay, timing delay. I will say TD, okay, timing delay in terms of number of samples. Okay, how many samples it has got shifted. So since over the year this is the one, and as soon as we reach I mean it reaches ADC, we are going to sample at finally we will have 30720 samples for this 20 megahertz signal. Okay, but out of this, okay, out of this samples there is a cyclic prefix. Even the main signal, both the cyclic prefix, let's say this much is a cyclic prefix, both cyclic prefix and the main signal both are shifted. So if we take only this much the signal where actual PRACH sequence is there, then that much is sufficient. So after removing cyclic prefix out of this 30720, finally the main PRACH signal, we have 24576 samples. Okay. So this much. Let me quickly verify that 24576. Okay, yeah, that is correct. So these many samples, we will take it for processing. But as I was mentioning in the beginning that mm, so sub-carrier spacing is 1.25, and whereas this is for the data. You can say QSCH and all other channels are having the 15 kilowatts. So there is a difference in the sub-carrier spacing, and that's why we need to upsample this to 15 kilowatts. So which means that if you divide this 15 kilohertz by 1.25 kilohertz, you will get 12, and basically you need to upsample 12 times these samples. So this will be done at the transmitter. It will be upsampled and sent. But whereas at the receiver, in G node B side, okay, mm, what would be done? It will be downsampled by 12 times, right? So this 24576 samples now will be downsampled by 12, and finally you will get 2048 samples. So that 2048, what do we do? Like we will perform FFT operation at the receiver side, right? So these are all happening at the G node B receiver, right? So I hope you got it. Like PRACH we are talking about, so which means this is sent in the uplink means from UA to G node B. So G node B is the receiver, UA is the transmitter. So FFT we are going to perform 2048, and finally we will get FD samples. Till now in this point TD 2048 was there. Okay, after doing this, this is so this is time domain, right? This analog signal. Once we do sample, this is also time domain, but this has got 30720 samples. Now from time domain, after removing cyclic prefix, we got time domain, 24576 samples. So to this we performed 2048 um, FFT. So from time domain 2048, we got 2048 frequency domain. Okay. No, actually, the moment we talk about F0 PRACH format 0, right? It has got 839 sequence length. PRACH sequence length is 839. So from here, actually, we extract only 839 samples, and this FD will be multiplied with locally generated frequency domain 839 samples. This is sequence locally generated, but this will be sequence plus noise with delay will be there. Okay, all the impairments, it has gone, I mean, it has come from the channel, but this is a locally generated sequence. So why do we do this multiplication? This is actually also called as okay. So this is correlation. Okay. So to find the timing delay, okay. I mean, to find the timing delay, if you want to do it in the time domain, we need a circular convolution. Okay, that would be costly, right, to implement a circular convolution and all. So circular convolution in time domain used as a can be used as a just multiplied in the frequency domain. So that's why in the frequency, this is frequency domain, this is also frequency domain. You just apply the multiplication operation here, that is nothing but correlation. And to convert back to time domain, you have to perform again IFFT. Okay, because timing delay we want in time domain, so it is better if we get back the signals in the time domain. So to get back to IFFT, see here we have 839 sequence only, right? Out of 2048 we extracted 839, but from 839 you can you will basically you can do zero padding, and you can perform 1024, that is one option, 104 IFFT, or you can go back to 2048 IFFT. This is a trade-off. You need to see which highest signal processing versus the accuracy you want. Let's say for example I have used 204 or 1024 for faster processing. um, then finally here you will have time domain 1024 samples. Okay. Okay, now after this, after this, um, you have 1024 time domain samples, right? So basically, after you perform the correlation, you are performing, you're doing energy correlation. So you will actually you have to perform power calculation. Power, you have to calculate the power, and then you have to see the what you can at this point you can see what you call as a power delay profile. Okay. mm, your signal. So something, okay, I'm just writing it in like this, but these are all samples only, right? So samples would look something like this. So at this point, you will have the highest correlation, highest correlation. So you will have the correlation at that point where there is a timing delay. Okay. So if you plot the output of this, you will see like this. In this, how many samples? So 1024 samples. Correct. Actually, from you had initially 2048. From there, you finally ended up having 1024. Now using some, what you have to do out of 1024, you don't know where is it. Mm, you have to perform peak search algorithm. You have to use an intelligent peak search algorithm considering the various configurations of PRACH. So that is a different topic. But sometimes what happens is that along with the one peak, we'll also have some kind of false peak as well. There could be second peak. So you have to also write an algorithm of first peak and the second peak, and you need to eliminate the second peak and take a proper decision. Otherwise, if you identify the second peak as the right peak, then it is a false detection. um, okay, that is when the PRACH goes wrong. um, so so those things are there. I will not get into those details, but now you got timing delay as TD1. Let's say TD1 value is, for now I will consider it as 16. Okay, 16 samples delay is there, or let's say for sake of simplicity, 32 samples delay is there. Okay. So now we have timing delay 1 is equal to 32 samples, but we know that this is coming out of 1024 samples, right? But what was the earlier sample? If I go back, okay, my earlier sample is 24576, right? So you need to map to that, and even from 24576 we came to 2048. Okay. So 1024 samples, I mean into 2, if I do, this will give me 2048. So here also you have to actually multiply by 2. It will 32 into 2. And again, we had reduced the samples by doing decimation by 12. So that also we need to add. So that's why you need to multiply by 12. Okay, this is your timing delay, which should be calculated at L1. Okay. Now the thing is that uh, what do we have to send this value to L2 layer. Okay. While sending, at L2 one should know how that is calculated and sent to UV. Okay. So it is G node B L2. Here the timing advance, okay, the timing advance values that to be applied at the UV, okay, it is in the integral multiple of 16 TS. That is why we need to send the value in this perspective only. So since the G node B L2 applies the received timing delay with 16 TS multiplication. So here to this value at L1 you have to divide by 16. Okay, so this is only this much information I have, why it is 16 TS, but you can try to figure out the more the more the specific reason of why 16 TS. Maybe the circuitry is designed like that to create the advance. So maybe it is like this, and this is the standard. I mean, everyone uses the same value. So which means this has to divided by 12 means this is, I mean, 16 means 2 or 4 48. So basically 48 is the value which will be sent to L2. L2 will to this 48 it multiplies by TS. This becomes the timing advance value now. Okay, this was timing delay. Now you have to calculate the timing advance required. Okay, it has its own equation. Okay, it has its own equation, considering the world timing advance world and some equation. I will not go through that. So it basically comes with timing advance new. If the world value is 0, then whatever value is there, that only will become the new. So this value will be sent to UB. Okay, TS, you got it right. This is a timing interval. TS is equal to 1 by Fs. This we already calculated. So I hope this concept is very clear. It has become lengthy because I wanted to explain timing advance, some basic concepts of how algorithm works. Those things were also required. So on a very high level, I went through the detector part. Let me try to see if I can bring in the detector part details in the upcoming videos related to PRACH. Um, or if you have any other specific question, you can ask so that I will try to bring those aspects as well. So don't forget to subscribe to the channel. I will try to bring in very good videos. Thank you very much.